Hey, what's up everyone? Jason Turley here, back with another video on PicoCTF. We're once again looking at the PicoCTF 2024 series of challenges, this time in the binary exploitation category. I've went ahead and I've solved a few of these challenges for Heap exploitation, for Heap overflows. So we see Heap 0, 1, 2, and 3 are finished. I just did not submit the flag. So in today's video, I'm going to showcase and do a walkthrough of all 4 of these Heap-based challenges. And I'm pretty excited for this because this will be the first time I've demonstrated any type of Heap-based exploitation or any Heap overflows or use after free vulnerabilities, anything like that on the channel. So if any of that piques your interest, if any of that sounds cool, then stay tuned. It might be a longer video because we're going to knock out all 4 of these challenges today. So with all that talking out of the way, let's open up the challenge description and read what it says. So Heap 0, the description reads, "Are overflows just a stack concern? Download the binary here and download the source code here. Additional details will be available after launching your instance." So let's click on the launch instance. If we really wanted, we could peek at this hint, and all it says is what part of the heap do you have control over, and how far is it from the safe variable? Interesting. So like I said, I've already solved these challenges. So if I look at my home directory, I do have challenge directories created for these. So let's just cd into Heap 0. If I do it ls-la, I do have everything downloaded, and I already wrote an exploit script, but I will be going over how to do that from scratch. Just a quick peek. It is a Python Pwntools script. So if Pwntools is anything you are interested in using, and that's just a popular capture the flag framework written in Python, I will be going over how to download and install and use this. So let's get started by just running the challenge binary, seeing what's going on, seeing what we're working with. We're greeted with a wall of text. It says, "Welcome to Heap 0. I put my data on the heap so it should be safe from any tampering. Since my data is not on the stack, I'll even let you write whatever info you want to the heap. I already took care of using malloc for you," with malloc being the memory allocator, which is a C library function just to allocate different bytes, different sections of data on the heap. So that's actually a big misunderstanding. They're saying, since my data is not on the stack, I'll let you write whatever you want. Just because something is located on the heap does not mean it's not susceptible to a heap overflow attack, which is a different type of buffer overflow vulnerability. So if we look at this segment right here, we see that it prints out the state of the heap. We have 2 addresses. They look to be the same. We have the address, and then it points to the heap data. The top address points to something called Pico, and the bottom one is Bico. So we have a few options in the menu. We can print the heap. We can write a buffer, so write your own personal block of data to the heap. Print something called safe variable. I'll even let you look at my variable on the heap. I'm confident it can't be modified. Okay, they're very sure of themselves here. We'll see if that's true, if we can't or cannot overwrite it. And then we have an option to print the flag. So if I just hit 1 to print the heap, it prints out that same block of diagram, that same block of information we saw above. If I hit 2 to write to the buffer, what does that give us? Another option pops up, data for the buffer. Let's just type in, please subscribe. Hit enter. Okay. Now let's 3, print out the safe variable. Safe variable equals Bico. Interesting. So let's hit 4 to print out the flag. Looks like everything is still secure. No flag for you. A little typo there. So let's exit and let's open up the challenge in sublime.txt just to see what's going on. And that's zoomed in way too much. So if we're reading this, okay, we see it's a C function. So we have these different header files added. Standard input, standard library, and some string functions. We see some variables, some macros being declared. So we have the maximum size of a flag is 64 bytes. The input data size is 5 bytes, and the safe variable size is also 5 bytes. We see a couple variables being allocated globally, so they can be accessed from anywhere. An integer storing the number of allocations we have, and then 2 character pointers, one for the safe variable, which we see here equals Biko, and one for the input data, which is our user input. So we see at the top on line 15, there's a check when function that calls string comparison. All it does is look at what's in the safe variable, and it compares it with this hard-coded value of Biko. And if they're not the same, if they're not equal to 0, then we win, and then it does some stuff to read the flag file and print it out for us. Otherwise, it prints that message that we saw earlier, no flag for you. We have the menu options, all 5 that we walked through before. A little call to flush, file system flush on standard out. Sometimes when there's not a new line character at the end of your printf, your print statement, nothing will actually get printed to the screen. It's waiting for something to flush the buffer, and you can do that with a new line or something like that, or you can just manually flush standard out. And then we have this function called init. So it's initializing all the different variables. We see that welcome message that printed out at the very beginning. Once again, it flushes standard output. And then here's the cool part. Now we're starting to allocate data on the heap. And all the heap is a dynamic way to allocate memory. So if you have the stack that we've covered multiple times in videos, where you can push and pop and add things one on top of each other, similar to like a stack of books or a stack of plates, the heap is different. And we'll get into that a bit more in later challenges. But for right now, that's all you need to know. And then, so we have our 2 variables, input data and safe variable, and they are being stored with the values Pico and Biko respectively. And then we can write to our buffer. We see here that it calls scanf. So it'll read in some memory. It'll read in our input and store it in the input data buffer. And we know that the input data buffer is only 5 bytes long, but there's no check. There's no check to actually see how many bytes we're entering. So we're using scanf. We should probably use something more secure than that. If I open up the manual page for scanf, what does it tell us? Usually these things have some type of warning saying, hey, you should not be using this function. So if we scroll down, do we see anything like that here? No, not necessarily. The scanf function reads input from the standard input stream, and fscanf reads input from the stream pointer stream. Interesting. So I know if we looked at the man page for get string, it'll actually give a warning of, hey, you should not be using this. So the issue here, the vulnerability, the flaw, is that there's no actual input check. There's no length check. So we can write as many bytes of data as we want. So why is that useful? So we want to overwrite this variable, safe variable. So it has the value Biko. We want to change it to something else. In this case, all it's checking is that safe var equals Biko. So if we change this to something else, we should win. So the next question is, how can we do that? How many bytes of data do we actually need to write into our input data variable buffer thing in order to overflow this Biko variable? So we're not sure. So what we're going to do is a process called fuzzing, where essentially we're just throwing random amounts of data, random amounts of bytes at this program and seeing if we can get it to overwrite Biko. So I'm going to select option 2 to overwrite the buffer, and I'm just going to slam in a whole bunch of A's and just see what happens. Smash the enter key, and now I'm going to print the heap one more time, and we see that Pico is no longer stored here, and Biko is no longer stored there either. So that is one way to do it. So let's see if I hit option 4 to actually print out the flag. It does say you win, which is nice, but then we get a segmentation fault. That's because I don't have anything called flag.txt here. So when it tries to open the file, it just gives me an error. If I wanted to very quickly just create one, please sub and slam that into flag.txt. Now we can rerun the challenge, hit 2 to write to our buffer, and then just smash A's. And now when we print the flag, it opens up our file that we created, please sub, and prints it out. So that is awesome. And if we really wanted at this point, we could connect to the challenge instance. But before we do that, let's look at how we can use Pwntools. So if you're not familiar, Pwntools is a capture the flag framework. It is a great utility written in Python, and it makes writing exploits for these kind of things a lot easier. So if you go to this website, just docs.pwntools.com, and we will be using Python 3 because Python 2 is no longer in use. It's deprecated. There's some great little instructions right here on how to install it. I do have a little script. If I go over to my my scripts directory, I do have one for install Pwntools, and all that is exactly doing what we saw here, right? I even have a link. All we're doing is updating, making sure we have Python installed and all these other utilities, and then we're upgrading our Python pip, and then we're installing Pwntools. So pretty simple. Pwntools, at first, it'll put all your information in like local bin. It'll put all your utilities here, which is not in your default path. So you might have to export your path variable. Just say path equals $path, and then add on like your home local bin. So that kind of tripped me up at first because everything is stored here in local bin, which is not in your default path. So with all that talking out of the way, let's actually create our exploits. I already have one, so I'm just going to delete it and then create a new one. Let's just open this up in Sublime. Sweet. So actually, I'm going to do this. I'm going to move my terminal over here, and I'm going to run the challenge, and then I can walk through the actual exploit as well. So hopefully you guys can see this. My big head's in the way. So the first thing we have to do is from pwn import all, and all this is doing is grabbing everything in the Pwntools namespace. And if we really wanted, we can add a shebang line. That's just good practice for writing scripts. User bin env Python 3. That way it knows we're using the Python 3 interpreter. So what do we need to do first? We need to create a payload, and then basically just send the payload, and then print flag. Those are like the three main things we need to do. We know our payload is simply just a bunch of A's. I'm gonna make these byte variables. I don't have it like fine-tuned, so we're just gonna slam in 40 A's. And now we need to actually send this payload to the script. And we can do that by making a variable called P and setting that equal to the process name, which is just challenge. And I do have some notes created here in Obsidian, so forgive me if I do kind of peek and look at them and whatnot. Obsidian is just a really good note-taking tool. So when we start up the challenge, and as we see on the left, we get this wall of text. So we actually need to tell Pwntools, we need to tell our exploit script to read in some of that data. We can just use the p.receive until function, and when we want to receive a certain number of data, certain number of bytes, we want to keep reading up until we get to this choice colon statement right here. So we can just grab that and slam it into our script. Now let's just send our payload. So send line payload. Actually, no, that's not what we want to do next. We want to select the option number 2 to write to the buffer. So we hit 2, and then the next thing that pops up is data for buffer. So let's make another receive line or receive until statement. Change this to buffer. Now we want to actually send our payload. So if we slam in like our A's here, what is the next option? We go back to the menu and it tells us to enter our choice. If we wanted, we can print the heap here, but let's select option 4 to print the flag. So we can just recopy this line. In order to print the flag, we want to send option number 2 or 4. So save and come over here and let's see if this works. Exit out of that. Let's run Python 3 exploit.py. And it does start up. We get this error. So I think once we send the line, we need to actually read the flag, receive all, save, and rerun this. Receiving all data, done. What am I missing? What did I do previously? Let's take out this receive until, and let's just actually just send option number 2 to the program, and then we can read in the buffer and then send our payload. Let's see if it likes that any better. Receiving all data, done. Interesting. What if do I need to actually just print this out? Control S to save it, rerun it. There you go. Okay. So you need to actually print out everything that you received. Otherwise, you're just going to get this generic logging statement, receiving all data. So cool. So it looks pretty ugly. We see all the option menus and whatnot that we saw before. But if we look closely here, we do see the statements of you win, please sub. So I did clean up the script just a tiny bit. We can start right away by just sending our option. We don't necessarily need to read in this menu option of enter your choice. You can if you want. So that's cool. That's how we make it work locally on our computer. But what we need to do is get it to actually work on this remote server. So we still have 12 minutes left. The challenge is still running. So we see here this netcat connection line. We see the host name and IP address. Pwntools is really cool because we can just use the process instead of using this process call here. We can comment that out. And now we can set P equal to remote, telling it we want to make a remote connection for this host name and IP address. Surround the host name in quotes and leave the IP address as an integer. Save it with Control S. And now when we run it, let's see if we actually get a flag. And we do. We can see here, Pico CTF, my first heap overflow. So we could clean this up if we want. We could probably use cut or grep and kind of parse out just the flag. But for the sake of this, I think that is pretty solid. So that's how you solve heap 0. Let's go over to heap 1 and run that challenge as well. So welcome to heap 1. I put my data on the heap, so it should be safe from any tampering. Since my data isn't on the stack, I'll even let you write whatever you want. So we see this is already very similar. In fact, when I first ran through this, I thought it was the exact same challenge. We see Pico and Bico written on the heap, and we have the exact same 4 menu options. So what's going on? If I just hit 2 to write to our buffer, and then I slam in a bunch of A's just like before, and then I go to print the heap, okay, we successfully overwrote both variables, both values. Now if I hit 4 to print the flag, looks like everything is still secure, no flag for you. So let's exit out. What's going on? That solution worked in the first challenge. Why isn't it working for this one? What's going on differently? Let's look at the source code in challenge.c. This is nice because it's nice having the source code and you don't really have to reverse engineer anything. It's nice to just be able to peek at exactly what is going on. Just like before, we see the flag max size and the input data sizes are exactly the same. But if we look here on this check when function, we see things are a bit different. Now the safe variable, it needs to exactly equal Pico. Before, all we had to do was overwrite it. Before it was Bico, change it to literally anything else, you get the flag. In this instance, we need to change the safe variable function from Bico to Pico. So what does that mean for us? It means we need to kind of tailor our exploit. We need to, instead of just slamming in however many bytes of junk we care about, we need to overwrite exactly as many bytes as we need. And if we read the challenge description, it kind of does tell us that. Can you control your overflow? Because before it was kind of just wild, it was just a mess. We could use 30, 40, 50 bytes, it didn't matter. So let's launch this challenge instance and let's come over here and let's try to figure out how we can only overwrite exactly as many bytes as we need. So let's run this challenge again. And I want to write a buffer But instead of just slamming in a bunch of A's, I'm actually going to use a tool called cyclic, which is available from Pwntools. Once you install it, you should get these command line functions at your disposal. So let's run cyclic 40, and it will just print out a nice pattern. So what we can do with that is grab it and paste it into our data for buffer, hit the enter key, and now let's print out the heap. So we see we overwrote our variable of pico, and then we also overwrote bico. So this is a great way to look at how many bytes you need to get to like a buffer. So if we were doing like a classic stack-based buffer overflow where you need to overwrite or fill your buffer with junk and then overwrite the instruction pointer and the return pointer, cyclic is a great way to do that, so you can know exactly how many bytes it takes to get to the return pointer. So you can do like a return to libc or return to win or execute your shellcode. So let's do cyclic, and let's look at the help. So cyclic with just a number will print out a pattern as we just saw. And then if we do tac L for a lookup value, we can get how many bytes it took to get to there. So cyclic tac L, and I don't want all 8 of these bytes. If I slam that in, it does cry and it does give me a warning saying the pattern must be 4 bytes. So instead of doing all 8, let's just do the first 4. And it tells us it takes 32 bytes of data to fill that buffer to get to this point. So let's now run cyclic with 32. Let's exit out of this, rerun our challenge, write to our buffer, paste in these 32 bytes, and these could be anything. They could have been 32 bytes of A's. And now let's append pico to the end of it. Now when we hit enter and we print out our heap, we see that we still have all our junk here, but now we overwrote that other variable with pico. So that's sweet. So if we hit option 4 to print the flag, it does say you win, and we get that seg fault that we saw earlier because we don't actually have a flag here, a flag file. So I'm going to remove my exploit and then rebuild it from scratch just because this is good practice for all of us. So now we have a separate exploit file, and we can just copy and paste a lot of this other challenge from heap 0. So that's another benefit of like writing down your scripts and not just doing everything on the command line. This is a good use case for like taking notes. So let's change up this payload a bit. Let's get rid of this. Let's say, instead of payload, let's say junk equals 32 A's. And now we need our our variable. So pico equals pico. And this also needs to be a byte value. And now our payload, let's set that equal to junk plus pico. And then everything else should be the same. The menu options were identical. So we're going to send 32 bytes of A's and then our variable. And if we want, we could do like some type of logging. We can print sending, let's see. Sending payload, save. Python 3 exploit.py. It's right here, sending payload. We see our A's and then pico at the end, and we do get our you win statement. So that one was pretty simple. Where's our host name? So if we grab this host name and the separate IP address, we can just come in here and we can slam this in. There we go, clean this up. Now rerun it. Let's comment out this one, comment out the process, and we want to run it remotely. So now when we run our script, it does work and it does print out our flag. We could probably do we could probably clean this up a little bit. Let's say retval equals p.receive all. Can I do a dot split? Split on new lines. And then just print out retval. If that works as I think it will, it should just print everything in a list. Oh, it's a byte. Since these are bytes, it doesn't support these string operations. That's okay. I'll leave that for a challenge for another time, just because this video is getting a little long already, and we do have 2 more challenges to solve. I was just trying to see if there's a way to clean this up, clean up our output. I'm sure there is, but for the sake of knowledge, I think this is perfect. This is good enough. So we do have that flag. We will just grab that and slam it into here. So that was the second challenge. Let's move on to the final 2. Heap number 2, let's launch that instance. Can you handle function pointers? And then we can download the binary and the source here, and I have that already available. So let's just move over into Heap 2. We can do ls-la, and we see that everything is there. Once again, I will remove that exploit code because I like building it from scratch. Let's run the challenge and see how this is different. So we already see our menu is a bit different. The heap isn't printed out automatically, and this time we have 5 options, with them being print the heap, write to a buffer, print out something called X. What is X? And then we can print the flag. So let's just start in order, printing out the heap. Okay, we see Pico and Bico. Make sure you guys can read that. So nothing really special. Okay, they're always Pico and Bico. What is X? 3. X equals Bico. Okay, write to buffer. Just use the spam approach of slamming in as many A's as we can. Hit enter, print out the heap one more time. So we did overwrite it. We did overwrite both variables. Print X. X equals A's, print flag. Seg fault. Why did we get a segmentation fault? A segmentation fault happens when your program tries to access a piece of memory that it can't. So for example, dereferencing a null pointer or trying to return to a return address that isn't valid. Okay, so we see some data allocated globally, just some variables, number of Alex. We see a pointer called X and then a pointer called input data. So input data is going to store what we write, and then X, we're still not sure what that is yet. We can see the win function here. Just make sure you guys can read that. We see the win function. It will print a flag. Okay, but how do we actually get to the win function? Check win. What is this? This is ugly. This is disgusting. This is hideous. Well, that's just the nature of programming in C. It's not always going to be pretty. It's not always going to be as nice as Python. If we wanted, we could clean this up just a tiny bit by formatting this better. So X is what is known as a function pointer. So we're already familiar with pointers because we saw these character pointers. We saw a character pointer to input data. And all a pointer does is point to a memory location, a memory address. So to explain it quickly, if we have our input data written as a character pointer, let's just say, so if we have some type of pointer, PTR, I know that looks terrible, and we set this equal to a string called hello, how this will actually look in memory is something like this. So we have our stack. We just draw a rectangle. And each character is placed at a different index in the stack. So we might have H here, and then underneath it we have E, and then L, O, and then this is a C string, so they end in a null terminator bit. So we'll just do this /0 or like null, just to specify, hey, this is the end of the string. So this is the first index, and all of these are only like 1 byte each because a character is 1 byte in size. So our pointer just points to the first index in our string. And if we did something like PTR +1, pointer arithmetic, PTR +1, it would now point to the E, right? So that's a bit about how strings work and how pointers work and the stack and whatnot. So I know this is a kind of ugly, it's a little awkward to look at, but essentially all this is saying is X is a function pointer, and we are going to dereference it. We are going to follow that arrow and see what X points to. In this case, if we scroll down, there must be some type of init function for X. Yeah, here we can see X is allocated as 5 bytes and it's stored with the value pico. So we could override it with pico, just like we did in the last example. But if we look at the win condition, it's not doing any type of string comparison. It's not actually looking for what the value of X is. It doesn't really care. In this case, what we need to do is set this function pointer to the address of the win function. So all we're doing is saying, hey, X, your value is the address of this function. And when you dereference yourself, when you call yourself, you will actually be calling the win function, and that should print out our flag. So there's a few ways we can go about doing this. First, we need to find the number of bytes it takes to actually get to that, to get to X, so we can overwrite it. It's probably 32 if all these challenges keep building off each other. So let's write a buffer, and let's just come over here. Do I still have that? Do I still have that pwn.cyclic pulled up? I don't. Let's just print out 32 bytes of whatever real quick. Slam that in, and now some random data, and let's print the heap. Sweet. So that proof of concept worked. It does take 32 bytes of junk, and then we can get to the X function pointer. So instead of having these as just X's, we want to actually have the address of the win function. And there's a few ways we can actually find that address. Let's look at the manual page for object dump. Object dump, display information from object files. So let's see, tag D, disassemble all. Let's give that a shot. Object dump, tag capital D on the challenge binary, and let's just try to grep out win. Nice. So we do get a memory address. Alternatively, if we do have the Radare 2 suite installed, we could also just use Robin 2. Let's look at the man page for that. A binary program info extractor. Pretty cool. That sounds very nice. If we scroll down and we look at the options, there should be one to do a disassembly. Okay, we can do a tag capital E to print out all of the exports, so that other functions, and we can pipe that into grep of win, and we do see here that same address from before, the same one we got with obj dump or object dump. So that is the actual address that we want to use. So to write our exploit, let's do the same thing. We can actually just copy heaps one exploit over here and then open this in Sublime. So you see it's very repetitive. So exploit writing, it's not like magic. It's not like anything reserved for like the truly elite. It is kind of just trial and error. It's reusing code that you've written previously. And it really can be formulaic, and it can be a kind of fun. So if I want, I can have the challenge instance up over here, and I have my exploit over here. Let me close out of some of these tabs. So our payload is going to be very similar. We're still going to have 32 bytes of junk, 32 bytes of A's, but instead of pico, instead what we want is the win address. So I can just say win adder, and that's going to be equal to P32, and then we can just slam in that address that we got from object dump. Grab this, slam it in. I don't know if that wants me to put it in quotes or not. It actually might need to be in hexadecimal. Instead of guessing, what I could do is just go to Pwntools and look at the actual documentation. So let's go to this quick search and just type in P32, hit enter, searching. Okay, let's see what P32 is. Okay, it doesn't give a very nice description. P32. Getting started, packing integers. Here we go. So a common task for exploit writing is converting between integers as Python sees them, and the representation is a sequence of bytes. Usually folks result to using the built-in struct module, which we have used before. So that's built into Python. You can just call struct.pack, and then you need to specify some type of size or endianness, because it could be different, whether it's an integer or a long or a double or a float. So Pwntools makes this a lot easier with this utility. So you no longer have to remember how you unpack different things. And you can literally just type in P32 for a 32-bit address or P64 for a 64-bit address. And then you can enter in the hex address that you need. So this is how the old-fashioned way, the built-in way of using the Python struct module, struct.pack, I for an integer, and then variable OX deadbeef. But we can see this is a lot easier to remember. So with that out of the way, everything should be good. So we have our 32 bytes of A's. We have our win address. I do need to change this to winaddr. And I think the menu options are the same as well. So option 2 to write to our buffer. Let's just confirm that. Option 2, and then we want to receive until it says the keyword buffer. We send in our payload, and then option 4 is still printing out the flag. So control exit, save our exploits, and now let's run it. Python 3 exploit.py. Did that work? We just get this empty string. Oh, that's because there's no flag here. Sure, echo path, the flag, .txt. Now we run that exploit. There we go. So it printed out my path. So it is actually reading the, it is calling the, it is, oh my goodness. So we are executing our function pointer correctly. It is calling the win address, and it is printing out flag.txt. In our case, flag.txt is just some random junk. So what we need to do now is connect to that instance, that server that's running. And again, a benefit, a beauty, a use case for Pwntools is it makes this a lot simpler. Because you can just say P equals remote and then the host name and IP address, or the host name and port rather. Smash the up arrow, and now we have our flag. Nice. So we only have one more challenge to solve. Thanks for sticking with me, guys. I know this is a bit of a longer video. In the last challenge, rightfully so, it is a lot harder. It is 200 points. The other one was worth, I think, about 100. Oh, there's also 200 points. So they are increasing in difficulty. So Heap 3, this program mishandles memory. Can you exploit it to get the flag? And if we want, we can pick at the hint. So check out use after free. So let's launch our instance, come back here, and same thing as before. Let's go to our Heap 3 directory that we previously created, and we already have our exploits created. I'm just going to remove it and build it from scratch. Let's run our challenge. Make sure you guys can read that. So freed, but still in use. Now memory untracked. Do you smell the bug? So a bit of a poem, a bit of a riddle. So we have more options this time. We can print the heap, allocate an object. That's interesting. We can print X arrow flag. So X is probably going to be some type of structure, some type of object, and we are accessing an internal variable it has, dereferencing a pointer perhaps. We can check for win. We can free X and we can exit. So let's just start by printing out the heap. So there's only one address. Before we had two. We had Pico and we had Bico. In this case, there's only one address, Bico. So we can allocate an object. What does that mean? Size of object? I don't know. 420. Data, please sub. Okay, did that do anything? Print x.flag. Bico. Check for win. No flag for you. I'm not sure why flag has an E at the end of it. Free X. 5. Did that do anything? Free X again? Error. So Double free detected in Tcache. What is Tcache? Let's grab this, slam it in. What is Tcache? Okay. Tcache attack explanation? This isn't a CTF challenge. Essentially, it's a really well documented C code. Okay, but what is Tcache? That's all I'm interested in. Let's find a different resource. Tcache is a technique. Tcache is a technique introduced after glibc 2.26. The purpose is to improve the performance of heap management. But while improving performance, it has abandoned a lot of security checks, so there are many new ways to use it. So it's a structure. It has two structures, an entry and a per thread struct. Okay, so this has something to do obviously with the heap and the heap allocation. I'm not sure how necessary or how relevant it is for our challenge, but we see here double free detected. So we freed X once and then we freed it again and we got this error of double free. So let's actually look at the source code, challenge.c, opening this up in Sublime, making sure it's nice and readable for everyone in the audience. So this is interesting. We see the structure, type define struct. It has three variables, A, B, and C, all of which are 10 bytes each. And then it has a variable called flag, which is only 4 bytes. In this struct, it's called object. And that's what we're setting X to. X is a pointer to an object structure. So the size of the structure is 35 bytes because it has 10, 20, 30, 5, assuming the compiler doesn't actually add any type of padding, because compilers, they like things to be even, because things are binary, 0 or 1, which is even. So it might round it up to 38 or 40, but we can assume, or we can try to guess, that this will be 35 bytes once it's allocated. We see our check when function. We see our good friend string compares being called. So we're dereferencing X and we're looking at the flag variable, the flag component, right? So we need to overwrite flag and have it equal to Pico, just like earlier in heap 1. And if we can set flag equal to Pico, we win. We see the menu, nothing really too exciting there. So let's look at our init function. We see that poem, that riddle that was printed out, flushing standard output. We're allocating the size of an object. So let's just say 35 bytes. And the X flag component, that section, is being set to Pico, and the rest of it is left uninitialized. So that could mean all these would just be equal to 0, or they could just be set to whatever was previously on the heap. And then here's our function to allocate an object. It asks us how big we want it to be. We can enter a size. Whatever we enter, it will allocate that amount of data. And then we can, it says data for flag, but it's not, we're not actually creating that same struct object, right? So X is one of these. X is a struct object. But what we're doing is we're just allocating however many bytes of data for the heap. So even though it says data for flag, it's not being written to like alloc.flag or anything like that. And then we can just free X. So how can we win? How can we actually overwrite this object, this X object? So in order to understand this, we need to kind of come back here and have a better understanding of the heap. So let me erase all of this and start from scratch. That looks, can I just home, new whiteboard, blank canvas. Okay, so we need to know just a tiny bit, just a smidge of how the heap actually works. Can I draw? So we saw earlier kind of what the stack looks like. So the heap is different. The heap exists as just one big slab of memory, and some of it will be allocated. let me draw. There we go. Some of it will be pre-allocated. So I'm just going to shade these in. These are in use. These blocks here have been allocated. Maybe this is like 50 bytes. So we had a call to like malloc 50, and maybe this big slab here is open and it has 100 bytes of available data. And then this slab is taken up, and right. So we've allocated something that's only like 12 bytes here, and then so on and so forth. So what are we doing? So when that function gets initialized, when we run challenge, and there's a call to the init function that allocates x, right? X equals malloc size of object. An object, as we said earlier, we're assuming it is 35 bytes. And once again, that's just because the structure has the 10, 20, 30, and then 5. So it has these 3 variables and the flag. So assuming the compiler is not actually adding any padding, then the struct object should be 35 bytes. So what the heap allocator does, what the operating system does, it's like, okay, you need 35 bytes of data available somewhere on the heap. And there's different ways it can pick an open free slot. It can do first fit. So if it's starting here from left to right and it's just going this way and it's scanning the heap allocator, the memory slabs, it's like, okay, so I have 100 bytes available here. I can just grab this. Or it's like, oh, over here, I have exactly 35 bytes of data. Let me just use this. So we could do first fit, best fit, worst fit. I won't break it down into all of them, but that's essentially the 3 main heap allocation like algorithms or techniques. So let's assume it's just using best fit. So I need 35 bytes of data for my X object. So it's going to plop X here, and right, it has A, B, C, and flag. So this is in use. This is not free anymore. So we have an option if we go back to that menu and we look at everything that we could select. We have an option to free X, and we have an option to allocate an object. So what we actually need to do here is call free on X, because when something is freed from the heap, it's not actually erased, it's not actually deleted. Like that data will still be there. All that happens is the heap will mark this as no longer in use. It'll say like this is available for someone to allocate data. So if this is marked as free, it's no longer in use. When we come along and we try to allocate our own object, right? This all depends on how the heap allocation strategy is. If it were using first fit, it might just put our stuff right here. But if we're assuming it's using best fit or something like that, then it will put it right here. So we want to overwrite this right here. Maybe I should pick a different color. So when we come along with our object, we want to overwrite this space. So what we need to do is free X, tell the heap manager that this right here, this block is now free. This block of 35 bytes is free. And then when we allocate an object, we're being silly and we just put a value in of like 420 or 430. What if we put 30 or 35 bytes? If it's using best fit, it's going to take this space right here to allocate our object. So let's give that a shot. Hopefully that diagram made sense. It kind of got uglier and more gross as I went along. So let's hit option 5 to free X. And now let's hit option 2 to allocate our own data. Let's say 35 bytes because that's the size of a structure. And let's slam in some A's. Let's be a little bit formulaic here. And let's just do cyclic of 35 and slam in 35 bytes of data. And see what happens. We hit enter, then we hit option 1 to print out the state of the heap. And look what happened. We overwrote Bico. And now it has our symbols. So let's exit and do this again. Hit up arrow, free the X object, allocate our own. Instead of doing 35, let's only do 30. Let's do 30 bytes of random junk. Grab this. So 35. But we paste in 30 bytes of junk to fill A, B, and C. And let's have Pico as the next set of bytes. Now, once we print the heap, it points to flag. So if we just do 3 to print out flag, it's equal to Pico. So all we did, where's Sublime Text? We overwrote this right here, this with junk, and then all that was left was to overwrite the flag variable with Pico. So now if I hit 3 to print the flag, or 4 to check for the win function, we do see that we won. So why is it important to do 35? If I do this again, if I free X, and now I enter a choice, allocate an object, 50 bytes, we slam in our data, and then Pico, and then we go to print out the flag. We see it's not overwritten, it's still Pico. So why didn't it work? My theory, my hypothesis is that the heap allocator strategy here is something like best fit. So there's 35 bytes of memory that were freed, but we try to allocate something of 50 bytes. You can't fit 50 bytes in 35, so it found somewhere else in that heap slab to allocate the data. With all that out of the way, let's open up Sublime exploit.py and let's write our last exploit of the day. Since all this stuff is very similar, we can just copy and paste in our previous exploit to save us from rewriting every single thing from scratch. We know we want 30 bytes of junk, and then we want to print out Pico. Pico goes Pico. Change this address here. And now the options are going to be a little bit different. If I run my challenge, the menu options have changed a little bit. And let's comment out the remote and just run this locally. So first we want to send option 5. Option 5 to free X. And then receive until we see that option choice. So we go back to the menu select. So here, let's change these comments. Free X object. Allocate data on the heap. And then print the flag. So let's actually clean this up a little bit. So in order to allocate data on the heap, we want to receive until choice and then send option 2. Option 2, and then we want to read until we get this allocation statement right there. So let's grab this and change that to allocation. And we want to send 35. We want to allocate something of 35 bytes. Something like 30 would probably also work as well. 35, send line, and now we need to send our data. And our data is going to be our payload. So p.sendLine payload, whatever. Now we're back here, enter your choice. And I think we just want to print the flag at this point. I guess if we wanted, we could do another p.receive until flag. Just to be consistent right here. And finally, to print the flag, we just need our receive until choice, and then send option 4. Yeah, I think it's always been option 4. I guess we could have this get flag, and then this is the actual printing of the flag. So let's look at this one more time. So we are telling it to send option number 5 to free X. That memory that was taken up on the heap, set it to no longer be reserved, so it's free. Send option 2 to allocate our own object of size 35 bytes, and then we just want to send our payload. So this looks good. We might have to do a little bit of debugging. Let's actually run it and see what happens. Nice, it prints out that we won. So we can come here. We have our instance already running. We can grab that host name and IP address. Slam that in. Just like that. come back to the terminal one more time, hit up arrow, and it does tell us that we won. Oh, it's still commented out. Let's fix that. Nice. PicoCTF, now that's free real estate. That's pretty funny. So that's it. That's how we solved that challenge. So that was a use after free vulnerability. If you want to like fix that and you're using like C and C++, stuff like that, where you have control of memory allocation. So after we free, once you free something, you should probably set it to null. So that way, if we ever try to use it again, if we ever try to dereference it, we would get a segmentation fault. So just for a bit of extra credit, you know, just playing around, we can use a tool called valgrind to look at the memory usage of these programs, see if there are any, you know, use after free vulnerabilities, see if there's any objects that are allocated that aren't freed, because our object that we allocated, we never called free on it. So it's just lingering in the stack. It's just lingering in the heap in the process memory. So we can use leak checks, leak, here, valgrind, tech help. So user for memcheck, leak check equals full. So search for memory leaks, and then show leak kinds equals all. So let's grab these. Show leak kinds equals all, and then leak check equals full. Challenge. So let's allocate our object, size 100 bytes, slam in whatever. Let's allocate one more, size 420 bytes, slam in whatever garbage. And now let's just hit 6 to exit the program. And we do get this heap summary. It says here, make sure we can read this. So heap summary, in use at exit, 555 bytes in 3 blocks. There was 5 allocs, so 5 calls to malloc, and only 2 frees. So there's 3 objects left on the heap that were not cleaned up. And it even tells us like where this happened on line 50 with the call to init. And then when we were doing our own allocations, we see a total of 520 bytes, and 2 blocks are definitely lost. So for a small program like this, it doesn't really matter. But if this were an application that was running on like a server and it just kept leaking data, at some point that process is going to run out of memory and it could crash. So that's really it. I think that's all I wanted to showcase for these challenges. Thanks for sticking around. I know this was kind of long, so I hope you guys got some knowledge, got some useful information out of all of this, doing these type of long form capture the flags, doing these heap exploitation videos. So yeah, that's really it for this video. Let me know in the comments down below what you guys thought. If you like these heap based explanations, if you like the diagrams, if you guys find stuff like this useful. I'll be back soon with more PicoCTF challenges and whatnot. If you guys noticed the shirt, if you're able to see it at all and you guys kind of like it and want to check it out, it is something I designed. It will be linked beneath the video below. It's super comfortable. So if you want to hack and style, look good while you're coding, check out the link for the clothing shop, the merchandise down below. As always, take it easy and see you guys in the next video.